Okay, so this is the last question we have for the review. A few weeks before the senatorial election between incumbent Senator Smirk and his challenger, former Governor Kraft, the senator's polling organization wants to know where he should concentrate his campaigning. So they take simple random samples of potential voters in the southern and northern portions of the state and ask them if they have decided who to vote for or are still undecided. Here are the results. So what they gave us here are the observed values. Do these data provide convincing evidence that there is a difference in the distribution of voters who have decided or are still undecided in the two regions? Use a chi-square test to support your conclusion. So hopefully by now you guys are realizing that it's a two-way table that they gave you. So we really got to figure out, is there a difference between the homogeneity or is it an independence test? Which one is it? Well, some of the things I'm leaning towards is, first of all, what kind of samples they took. It says they took a simple random samples. Oh, I guess it didn't say a random sample. It says simple random samples. So it kind of looks like they took a sample in the south and then they took a sample in the north. And something else that kind of reiterates that is it says, do these data provide convincing evidence that there is a difference in the two regions? So this is all pointing out to me that I'm comparing these two regions. And if it's a comparison type of test, that means it's a homogeneity test. Okay? So, knowing that it's a homogeneity and I'm looking for the difference, here is how I said my null and alternative hypothesis. My null hypothesis is the distribution of voters who have decided or are still undecided is the same between the North and the South. So remember, whenever we're looking for a difference, we have to start by assuming that they are the same, okay? Now, what about the alternative then? I'm trying to show that there is a difference. In fact, I'm trying to see which one is different so I know where to, to do my, my efforts of trying to get votes. Well, the alternative is the distribution of voters who have decided or are still undecided is not the same between the North and the South. So we're assuming they're the same versus we are assuming that they are not the same. So one last thing that I didn't end up typing in here is the alpha level. Just make sure you say it at some point in the state portion. We will use a alpha level of 5%. So because I identified up here that it's a homogeneity test, we're going to say that in the plan step. It's a chi-square test of homogeneity. We are comparing the North and the South. And then we got to check our random conditions. Well, up above, they said they take simple random samples. So I just kind of quoted that. Simple random samples of potentials in the South and in the North. Notice I'm talking about they took the samples in the South and the North. This is kind of the way I'm talking about both samples. That's the thing about homogeneity is remember, you're taking multiple samples. So when you're doing the conditions, you have to mention it for both samples. Which means when I do my 10% condition, notice I did my 10% condition twice. Assuming 176 is less than 10% of all the voters in the North, and assuming 200 is less than 10% of all the voters in the South. So kind of pay attention to the way I said that. I did it twice, once for the North, once for the South, once for each sample, okay? Now, what about the large sample size condition? We got to make sure that all the expected counts are greater than or equal to 5. So I'm going to go back up to my chart, and thankfully they gave us the totals already. So remember, to find the expected value, you do your row total, 176, times your column total, 264, divided by your grand total, 376. That's how you would find this first value. In fact, I did it all for you. I wrote expected counts in red, and I put all of the expected counts in red, so you can verify those as well. If I wanted to do 148, I'd do the same thing. 200 times 264 divided by the grand total of 376. Okay, so you guys can verify your expected counts. Now, one other thing I want to point out is my smallest expected count is 52.4. So I said that in my conditions. I said the smallest expected count is 52.4. Therefore, all the expected counts are larger than 5. So I went ahead and showed my large sample size condition. So now what do we have to do from here? Well, now we're going to go ahead and do the work. Okay, so just like the last test, our goal is to figure out the p-value using a chi-squared distribution. So the first thing we have to do is figure out what that chi-squared value is so that we can figure out the p-value underneath that curve. We do that by finding all the observed minus the expected squared divided by the expected. We do that for every single term, and then we add them all up. Now remember, I want you guys to kind of show your work. How'd you do this? Now, since there's only 4 of them, I would just go ahead and write all of them out. Now, I have the paper in front of me. Hopefully you do as well. The first observed is 116 minus the expected I wrote up there above was 123.6 squared divided by 123.6. Plus, I'm going to go down my chart. I'm a vertical person, so I'm going to go down my chart to south and decided, and that's 148 that we saw minus the 140.4 expected. We square that and we divide by the expected. Plus, I'm going to move on to north still undecided. There are 60 minus the 52.4 expected squared divided by that 52.4. And then the last one is the south undecided. We saw 52 compared to the 59.6. I'm having to squeeze it in there. We're going to square it divided by the 59.6. Sorry for my messy handwriting there. So there was only 4 of them. I just decided to write them all out. If you wrote the first one plus ... the last one, that is sufficient. That is fine. Now, how did I do that in my calculator? Again, I'm getting all of those values here. I did this one minus this one squared divided by this one. And then I moved down. I did this one, these two next. And then I compared these two, and then I compared these two. So in my calculator, okay, here's my calculator. You can see I put the observed going vertically, and then I put my expected. And then remember how you do the formula. Up, way up here, I typed list 1 minus list 2 squared divided by list 2. And I have my components. Okay, so I'm going to go ahead and write those down just because I personally like to write them down. I like to know what my components are. 0.467 plus 0.411 plus 1.102 plus 0.969, okay? When you add those all up, remember you can do that by going to, I'm going to click out of that. We can go to Stat, scroll over to Calc. Option 1, we want to tell it list 3. So when I go down to find the sum, it's right here. That's not a very big sum. It's 2.95. So the chi-squared is 2.95. Huh, interesting. Okay, not a very big chi-squared. So I kind of feel like I know what might happen, but I don't know, let's keep seeing. We got to figure out the p-value by doing chi-squared CDF. We got to actually figure out what that p-value is. So if the lower bound is that chi-squared of 2.95, remember the upper bound means it goes on for forever, 2.999. And what's the degrees of freedom? Well, we have a chart here. So if I chop off the last row and the last column, I only have one data piece left. So it looks like I have a degrees of freedom of just 1. Okay, so there's your lower, there's your upper, there's your degrees of freedom. When I type that into my calculator, I'm going to go to second distribution. I'm going to scroll down to not option 7, but option 8, chi-squared CDF, and I'm going to type that in. It was 2.95 with 999 upper and just 1 degrees of freedom. Okay. So remember, if you have the older calculator, just make sure you put them in there with commas. I'm going to go ahead and hit enter, and I get a p-value of 0.085, or I guess it rounds up to 6, 0.086. So 0.086 is my p-value. Okay. I feel like that's not too small of a p-value. I notice that it's greater than 5%. So notice how I say my conclusion. So assuming the null hypothesis is true, and I went ahead and abbreviated this, the distribution between north and south is the same. There is a 0.08, I guess that should be a 6, 0.086 probability of obtaining a chi-squared value of 2.95 or higher purely by chance. This provides weak evidence against the null hypothesis and is not statistically significant at alpha of 5%, and that's because this 0.086 is bigger than 5%. Therefore, we fail to reject the null hypothesis and cannot conclude that there is a difference in the distribution of voters who have decided or are still undecided in the North and the South. So in other words, we really don't know where we should have our campaign efforts, in the North or the South, because there really wasn't too big of a difference. Okay, do I need to write the follow-up analysis? No, because I did not reject the null hypothesis. However, if you look at the last portion, okay, this last portion might get a little bit tricky, and I don't want you guys to worry about it too much, but it says the pollsters are concerned that while all 200 people in the South sample responded, there were 24 people out of the original 200 in the North that just didn't end up responding. Like, did you notice that the total was 176 in the North versus the 200 in the South? That means 24 people in the North just never sent back their response. So here's what I did with our data, is wanting to know if we ended up hearing from those 24 people, would we ended up having a difference after all? Is it possible that the opinion of these 24 people would change the pollsters' conclusion? So is there any way that those 24 votes would change our decision from failing to reject to rejecting instead? So here's what I did. I went back up to my work up here and I said, which one was the largest component? Because usually the largest component is the biggest factor for why you rejected the null hypothesis. So my largest component was this. Now that really didn't affect it. I still had a large p-value, but noticing the way I typed that in, I went vertically. So that was 1, 2, 3. That was this total in the North. So basically, I want to know, what if I made the difference in this area even larger? So maybe let's stick all 24 people that did not respond in the North. Let's say that they're all undecided after all. Let's see if we can make that component even larger. And maybe the North is where we need to decide to send our people for campaigning. So here's what I did. I know you guys can see some of my work already, but I said, let's add all 24 people to that North. Let's try to make this component bigger. If I did that, that ends up turning my number into 84 people in the North who are still undecided. Now, I had to kind of change things around. That means we no longer have 176 people in the North. We now have 200 people in the North. And we now have 136 people who are undecided out of a total of 400 people altogether. So I recalculated my expected counts to 132 and 68 with these new totals. Now I'm not going to go through all of the work that I did above, but when I did all the work, when I did observed minus expected squared over expected, observed minus expected squared over expected, observed minus expected squared over expected, and so forth, and then I added up all those components, I ended up getting a much larger difference there. I got an 11.4 as my chi-squared. And so when I did my chi-squared CDF, look at the p-value I ended up getting. Whoa, the p-value really shrank when we put those 24 into the area with the largest component. So what do you think? If I put those 24 people in and they all decided to be undecided votes, do you think that changes the decision? I would say, yeah, it is possible that those 24 people would change the opinions because the p-value ends up getting extremely small. What that would tell me is, let's send all of our people to the North because there's a lot of people undecided, and maybe we can go ahead and get some of those votes. Again, this area is not a huge thing to worry about. I really just want you guys to focus on, do you know how to do the general chi-squared test? Did you figure out that it's homogeneity? Do you know how to do all these calculations? I feel like this bottom part is a bonus. So hopefully you guys kind of understood the bottom part. And I wish you guys the best of luck on the test.